we have something which can give us an estimation about the quality for added noises. Last time we also had the intrinsic dimensionality, or last year at a talk here for computer vision noise, yeah, so Gaussian noise, salt and pepper noise, and so on and so forth. But this also works here for much more complex noise where no mathematical model is known, like weather conditions. Yeah? So also there it can be applied, which is, I think, a great benefit. But again, of course, not yet perfect and not yet solving everything, but at least a step into the direction of estimating the robustness for different weather conditions. Which, looking back, is of course very important for the agricultural use case, but also, for example, for driving in pedestrian zones. Yeah. That's it from my side. Thanks for the attention, and if you have any questions, please feel free to ask.
So, I want to ask about are there any further architectures you are considering to use? Like you mentioned transformers. So currently you said that you are using faster arcane, and
Yes.
so as compared to faster arcane, what do you expect how transformers
Okay.
be?
So we have tested it also with other architectures, not only faster CNN, but they were all CNN based. There we did not observe any big change. It more or less performed always the same. For vision transformers, like I said, if you have something like DTR where also there's a CNN involved, I of course expect something similar. What literature at least shows that in vision transformers the features are much more globally oriented, let's say. Yeah, so they are less based on the local thing, but more globally. I would still think that there should be a change in the dimensionality, because of course still things should, so the dimensionality of course just represents or checks what is needs to represent it. It doesn't matter how it is represented with which features. So I assume it stays the same, but we have not really tested it. Again, I assume it stays the same because still certain features are needed, yeah, or parameters are needed to be represented in the vision transformer.
Okay. So when you talk about dimensionality, could you please elaborate on that? Basically, like if you are just talking about where the network is currently focusing on, right, in object detection, that as you have shown in the slide, it was there were a sort of graph cam looking graphs, right, images. So what did you use for those visualizations that where the network is currently focusing on, and can you elaborate on the dimensionality aspect of that?
Yeah, so it's a little bit two different things. So this is not directly related to the intrinsic dimensionality, right? This is more what other things already exist. And of course, to check if the object detection works or not, it's kind of natural to take a look at the proposed regions of localizations. Yeah? And so here, more or less, we just took a look at the outputs of the region proposal network. Yeah, in this case, again, a two-stage detector. Yeah, so we more or less just took a look at the things that are happening here, what are the outputs of this. Yeah, and for the visualizations of the gradients, this is, of course, so here on the top row or on the second one, this is also happening here in the backbone. Now, of course, maybe what it's focusing on, the approach of the intrinsic dimensionality, does not consider the things inside the proposed regions. Yeah, it mainly, maybe it's not mainly. Yeah, of course, here in the end, a little bit. Yeah, but this is usually not where we observe the changes. We still observe them in the initial layers, where it's actually independent of the localization problem. Yeah, and only relevant of the feature, on the feature level. So there we have not checked how the, let's say, the dimensionality changes for the pooled features. Yeah? I think maybe this was the direction of the question, so this we have not yet considered. Yes?
In the first half of presentation, you showed a picture of point cloud.
Yes.
So which do you use for that point cloud for generating it?
So I assume this one. So again, the turquoise one, this was recorded with a laser scanner. It was an Auster OS0 with, I think, 128 lines. Here, I think we have a ZED camera, stereo camera, and here two real sensors.
So
And yes,
why didn't you use the LiDAR sensor for that point cloud generation? Because they are more accurate and much more efficient than photogrammetry.
yeah, okay. So the Auster, it's a 3D laser scanner, point cloud scanner, right? And so we just combined them. Usually we do this to add some context to our maps data. Yeah, so because when we do a detection or classification or segmentation, we usually do this, of course, for the camera image. And if we have also a stereo camera, it's very easy to map this back again to the point cloud. If we, of course, only have the point cloud, then we can also do this more or less with just a mono camera, but it's less precise and more difficult. If we have both, then we can get the context from the stereo camera and map it into the point cloud, so we can enrich the point cloud with more context. Yeah? For the, we still keep the data of the 3D laser scanner, but we add on top the data of the camera to get the context. Yeah? That's the main idea. Yes. Other questions?
So I'm gonna ask again about
Sure.
what do we mean by actually intrinsic dimensionality, right? Are we talking about the spatial dimensions, or could you please explain on that?
Yeah, so of course the actual spatial dimensions, this is very big, so this could be for a normal image, I don't know, if it's 800 times 600 times 3, yeah? That's of course, so that's not the intrinsic dimensionality,
Okay.
yeah? The intrinsic dimensionality is the number of features or the number of parameters needed to represent the data.
Sure.
Yeah, so right, if we have a circle or ball in 3D space, we maybe only need a subset of the parameters. Yeah, if we have a 3D ball in 200 dimensions. Yeah? Now, of course, this number of features needed to represent the data depends on the transformations before. So if we represent our data, for example, in a Cartesian space, yeah, let's say our data lies on a circle, yeah, and we want to represent the data in the Cartesian space, right? Then if we have it, want to just specify things on a circle with a certain class and everything not on the circle with a different class, then we need a lot of planes in the 3D case, in a standard 3D Cartesian space. In the case of maybe a spherical coordinate system, we only need one thing, the radius. Yeah, so there are only one dimension. Yeah, so this is, of course, this is what the intrinsic dimensionality means, the number of parameters needed to represent the data. Yeah, for these image things or features, this is of course a bit more difficult, yeah, because it's a complex mathematical manifold, just theoretically, which is very difficult to really perceive, yeah, or just calculate, visualize, yeah. It's not so easy to do that, or straight or impossible. But this intrinsic dimensionality, yeah, this should just estimate this, or this algorithm should just estimate this on a local level. Yeah, so at this point, or at these points, this is the local dimensionality. Yeah, so at this local point, we need this number of parameters to represent it. It's not a global dimensionality estimation, which would say how much is needed for over the whole distribution. Yeah, usually there exists also approaches for this, to calculate this, but they are even more computationally expensive. So this is why we had to focus on the local one. And estimation, yeah, difficult to calculate, but estimation also seems to be good enough. Okay.
Sure.
One question, have you tried this with the real world data, or is it only with the simulation that you are doing?
We also tried it with real data, compared it there. There one also notices similar effects, but they were not as strong, probably because the images look more similar, I would say. Yeah? So when we take a look at at here, so for example, for the real data, it's on the campus, so the same campus. I mean, of course, it's also true here. Yeah, but let's say the background changes, but maybe not so much how the overall view, the overall image looks like. I think this is a little bit stronger for the simulated case, which is probably why these effects were a little bit bigger, but one still could observe it also for the real data case. Yes?
Should not we focus on some generic pre-processing technique instead of going with the model? As you discussed previously, that you are using different model, right, to see the variation or something. Should not we use some generic pre-processing technique for this?
So, I mean, general preprocessing technique to be more robust. That we also tried actually for, but this is much more difficult for generic weather or environment conditions. Yeah, with the preprocessing you might get rid of rain, of snowflakes, but if you then talk about autumn or general hue or fogginess or everything, then it gets a little more complicated. We actually also tried to have some generated adversarial networks to get rid of this and get some neutral images, but it did not perform as well as we expected it to perform, but this is also something which we try to increase the robustness, but to estimate the robustness, which is what would be needed, for example, if you want to license some vehicle, some approach to be used in some industrial application product, then you still would need to be able to estimate the robustness. Yeah, so for example, you have, I don't know, object detection in your car, you want to also use it while it rains, then you would need to prove that you have the same robustness in rain as in sun, let's say. Yeah, and then for something like this, one still needs the robustness estimation. Yeah? So that's the idea, to not only improve the robustness. Yes.
As compared to the other normal techniques of vision, is this time saving, more time saving as compared to them?
So most approaches which we see, I think they still need a lot of human in the loop, let's say. Either you need the labeling, or when you visualize the features, you still need to take a look at it and see what is different. And very often it's not so clear. Yeah? That things are different. Yeah, of course. I mean, the results of feature visualizations in the papers where they are, I mean, very clearly they have a big effect, and you can clearly see what is going wrong, and that you need to change the data, improve or reduce the stride or whatever. But you still need to take a look at it, and you need a lot of expert knowledge really to see what is going wrong. Yeah, but for the intrinsic dimensionality, you can more or less compute it and kind of rule-based check it if something is changing. Yeah, so that is there also a benefit from the computational cost, of course, much more time-consuming.
So let's say if we were using it for a medical purpose, for example, in that case we need robustness in the model. We need like 80% accuracy because we will not compromise on the accuracy. So is that model applicable there? And will time become an issue if we are looking at a million cases?
So, so the idea is, so it's not model specific. So the application or the methodology can be used for any CNN-based model, and the idea is not to improve the robustness of one model to achieve their one certain quality. Yeah, but let's say you have your, I mean, I'm not expert in medical imaging, but let's say you have verified your approach for a certain type of MRI scanner, and there it works with 90% accuracy, and now you change the scanner. Now you maybe don't want first to record data, label data, or I mean, really use it on the actual patients, but you maybe want just to hear how it would change if you do it. So then you calculate the robustness and see that it changes. So it could also be applicable there, but I mean, this is far from what we do, so we haven't tested this, but I assume
so it's not applicable in the field, it's just a point of research, and it's basically needed for some sort of computational reduction, human effort reduction.
So it should reduce the human effort, or it can reduce human effort, but it's still needed for the robustness estimation, independent of the application. And so we apply for this. It can also be applied for medical imaging. Just we haven't tested it there. But the idea to estimate how robust we are, the methodology is application independent.
So how long did it take to train this data?
Okay, so I mean, training the network on the object detection, that's, I don't know, a couple of days for these different modalities. The calculation for all of these different cases, so the three real cases and I think 9 simulated cases, this took in total, I mean, it took around about 1 month, but not permanent training, yeah, but that's what we had. But again, if you more or less do this all the time on the fly when you go somewhere new, I still think this is applicable.
So would pre-processing work
I think I will
for
stop here
reduced
Yeah.
time.
because it's taking a lot of time. We have another speaker, so maybe we can continue later on at some point. But for this, I would thank Mr. Axel. Okay, with that we come up to our next speaker, Mr. Eike Gassen. Some of you probably have already saw him last year. Introduction of him. Eike Gassen studied mechanical engineering at the Technische Universität Kaiserslautern in his bachelor's degree and mechanical engineering with applied computer science in his master's degree. During his studies, he focused on robotics. The topic of his master thesis was the conceptual design of a vineyard robot in a steep slope viticulture. In addition to that, the comparison of different kinematic concepts, a modular design of the entire robot was discussed in order to achieve the most extensive use in the vineyard. Mr. Gassen has been a member of our lab since September 2021. His research focus here is on innovative mechatronic systems in agriculture. So I would like Mr.
Hello, good evening everyone. Thank you for the introduction. And I would like you to give a short overview or an excerpt of our agricultural project we are doing right now at the RR Lab. So I'll start with two projects in general. It's the already introduced project Nalamki, AI in agriculture, sustainable AI in agriculture. I will introduce the FarmBot. It's a modified tractor, and in the second part of the presentation I will shortly talk about the steep slope vineyard robot we are working on. So first we got this FarmBot, here a picture on the right hand side. It's a standard tractor from the John Deere company, and we got the following task. We want to deliver a small tractor in an optimized way for smaller scale farms, because right now these highly autonomous tractors are in general very large, huge machines for huge farms, but there is not such many robots for the different smaller farms. And of course, we want to tackle with this small tractor. It just has around 30 horsepower, so it's not. This tractor has a weight of 1.3 tons, so really a light-weighted tractor. And the goal of our modification is that this tractor drives in an autonomized manner, so without human steering, and also fulfilling tasks. So we want to apply attachments and fulfill tasks in and on the field. So here just general sensor setup. On top we got the GPS, the Starfire from John Deere, so very famous and often used GPS. We also added on the top a LiDAR sensor to get an overview of the environment, so a 360-degree LiDAR sensor, and also a really good stereo camera pair. So this two, which looks in the front, one stereo camera for backward driving. You got a question? Backward driving, and here in the back we got a box where all the electrical stuff is inside, so power electronics, the battery to get the power for this system, because it's relatively power consuming compared to the power which the battery of the tractor itself delivers. And of course we have all the safety equipment in the box behind the tractor. So as I mentioned, the task in general of course is the autonomous driving and controlling the front and the rear edge, just for understanding. this is the frontage, and of course in the back you have also not visible from here. You got such a suspension where you can mount the attachments which are doing the work. This is again the general idea of our work on this robot, and what we are doing or how we are doing it is that we start in a simulation. Here the left image, you got a simulation in the Unreal Engine where, as Axel said, we want to get the rough idea of, for example, where to mount sensors and what data the sensors deliver. So we got I think this is also good to know, we got also the sensors and their input and output data simulated in the Unreal Engine. So we can estimate and can have a rough idea of the sensor data the sensor gets if we mount it. For example, this is a real photo here on the top. So we got a really good understanding of the data we will get in the real world. And here you see the first step in developing. This tractor right now is driving with remote control. So as you obviously see, no one is sitting up in the tractor, and we are steering it with a remote control with a joystick. And of course, there we mounted to this general tractor the company John Deere delivered to us a steering motor and also velocity control. And these are the first steps for really working on it, because afterwards the next step is to mount an attachment on it, like a plow or something, put it in the ground and let it work in an autonomous way. But as I said, this project is ongoing, so this is the stand of this is where we are right now, and we want the next step. As this prospect, want to define different applications, because it's hard to do this in an autonomous manner for every application. Because if you want to, for example, plow a field, it's a complete other thing than to apply spraying agent. And therefore, we want to use a behavior-based approach of controlling the tractor as well as the attachment. This is also what Axel introduced. It's a way of controlling it, and ongoing work is to specify the use cases. So far to the first. This is the second project I want to introduce. This is a vineyard robot for steep slopes. The abbreviation is AVOS, so Autonomous Vineyard Robot for Operating on Steep Slopes. In Germany, we got this steep slope vineyards with an inclination up to 70 degrees. So very steep slopes where it's very hard to work all day, and especially in the summer. In the summer it's very tedious and hot, and the people don't want to do the work by hand anymore. And so we tried to develop a lightweight robot from scratch for the farmer, for the winemaker, and to do this in a realistic way. That means to do it for not high cost and affordable for the winemaker. And the first step is that we use here a winch with a steel rope to climb up the steep slopes. And we want the winemaker to use it in as many works as possible. So we define special applications here. In the picture you see this red thing here. There's a tank for a spraying agent. So this means if we drive the slope up and down, we apply spraying agent to protect the plants, the vines. And of course, to drive the slopes up and down, you need to drive the vehicle, you need to know where the vehicle is, where it already sprayed spraying agent. And yeah, I think in the following slide I will here again a bit about the applications. We want to make a forecast of the yield. We want to fertilize the plants. We want also do, let me say, lightweight mechanical works like mowing, because if you're working in steep slope, the physics behind it is heavier, is more weight you have to put up and down, there's more energy you need. And the disadvantage, of course, is so whether you can do everything and it's a very high, heavy vehicle where you need a lot of power, or B, have to, in any case, need a lot of power. So you need to change the batteries all over the time, because we want to do it an electrical vehicle, not with a combustion engine. And because of that, we made the decision that we have a maximum weight for the vehicle of 150 kilograms, but therefore we got the trade-off that we can't do anything like plowing. There you need a lot of energy to put it up and down, but we can make a lot of cycles driving up and down the slopes, which is of advantage for the winemaker, that he doesn't have to change the battery every hour or so. And here about the working principle. So this Rhineland robot is mounted on a winch, has a stroke where it drives down and up again, because if you are fixed on the wire, you can't just drive to the next row, because there's a wire which will destroy the plant. So you drive down. In this case, you apply the spraying agent, drive down, and the idea is to the second stroke, when you drive up again, you can do another work. And then you drive back to the platform, in this case, a trailer or a tractor, and you drive to the next row. And there it goes in the second way, again in the same way. And yeah, let me say, zoom a bit into the robot. Here a short overview. We got a stereo camera in the front, the stereo camera in the back, to just see where we want to drive, and to see the space between the plants and also part of the plants. We have here the winch with the speed cable. We have also two cameras on the left and the right side for seeing the foliage of the plant and the plant from the side view. And yeah, we have also an acceleration sensor, just to get knowledge about the placement of the vehicle in the vineyard itself. And here, to come back to the question before, we got here, as Axel explained, the LiDAR sensor fusion with the stereo images and the information about the stereo images. Of course, everything what Axel said is completely right, but especially the most important case, why we didn't, or why we used all of this, because we wanted to know what is the most, the less expensive, cheapest solution of how to get a functional system. Of course, we can mount this LiDAR sensor for nearly 10,000 euros on top of this robot, but then it's not affordable for the smaller farms. What is in general the goal of this robot? And so we decided after this test run that we are just using the stereo camera, so which is producing the screen distance image, and the two cameras on the side instead of the better working LiDAR sensor, because of the money the LiDAR costs. And yeah, I think I can explain a bit more because Axel already started explaining it. Here on the bottom left, we got a map where you can see where the vehicle is able to drive on. We got here, as I said, the rows of the vineyard, which is red, because the robot is not able to climb, or should not climb the vines itself. So the green area, the robot can drive, and the red area, the robot should not drive. And yeah, I think in general, most other parts are explained by Axel already. And here the realization. I think I already started with this. We started with the kinematic, got the first runs on our hill in front of the university, so not in the Rhineland itself. And we realized that it's not really easy to work just with a differential drive like we're doing here, so steering with different rotation speeds of the wheels. And now we are doing it with a steerable wheel, so 3-point. We changed 4 wheels to 3 wheels, and also we got a very heavy winch with 50 kilos, with the upper limit of 150 kilos. It's of course too heavy, and we started designing a lightweighted winch. So this winch is now already not just designed but already mounted. It's just 8 kilos, so we lost 42 kilos, and now we got a second mock-up of this vehicle. And this is the state now, and also here we want to extend the range of applications, as I already mentioned, and modify the control of the robot. Here we got the different stages of the robot. First, just a platform where we started to collect, as I said, here already with the LiDAR sensor and with the stereo cameras, to get the knowledge which sensors we really need and which we don't need to not waste money, because as I said, we want to do a cheap vehicle for the farmer. And the last one, video out of our archive of the testing. So not everything goes perfect in this testing phase. There the safety chain doesn't work very well. But in the end, nothing really bad happened. And so far to our research and our work on the robots. Thank you for your attention, and I'm ready to ask questions.
So, in the case of the tractor, how are the drive commands being fed physically to the existing drive assembly of the tractor?
You mean from, you go back to the slide.
Like if the model decides that the tractor has to move left now, we are not obviously physically moving the steering wheel left. How are we passing this command to the drive
This is
assembly?
the behavior-based architecture, so you mean the tractor decides to move left?
Yeah, so how are we like passing that command physically to the drive assembly of the tractor?
Physically, there is a motor inside.
Okay, so is the tractor electric?
No, we have. So that is the point. We maybe I put the picture here. We had some to do some additional tuning on the tractor, or additional work. So there was a third party which installed a steering motor with sensors which measure the inclination, the angle between the axes, and we give with the angle. We put pressure on the valve, which steers hydraulically the wheel. Yeah.
There is a possibility to steer.
Yeah. Exactly. So we have two ways. You can do it in an autonomous way by the motor, by this steering motor, which puts pressure on the hydraulic cylinder, and also we got the possibility to steer via hand, which is doing the same, but of course the manual steering is as a high
But you cannot steer more, in a limit you can steer.
Yeah,
You cannot
exactly.
go very steer.
Yeah, you have the
Because there is you are connected with a
yeah, so you mean that the angle of the
yeah,
wheel?
yeah. I mean this.
Yeah, this is